Alright, this is EET112 Lab 4, and in this video I'm going to show you how to do the inductor circuit measurements. So this is where you have the function generator tied to a 1K resistor, which is then tied to a 100 millihenry inductor to ground. So it's an RL circuit. First thing is I've set my scope. I'm going to hit the default button so we all start off with the same scope setting. And then I'm going to program my function generator to a 10 volt peak to peak square wave with an offset of 5 volt DC and a frequency. I'm going to set mine to 800 Hertz. And that was roughly what I got when I did that calculation that the lab document recommended, which is for your frequencies, set your square wave to about 1 divided by 15 tau, whatever tau you calculated. So for me, and probably for you too, 800 Hertz is about right. Doesn't matter. It can be higher or a little bit lower. Just you want to see a full discharge and charging of your inductor, and that'll be obvious once we look at the waveform. Okay, so now I'm going to measure the function generator directly with the scope probe. So it's not hooked up to the circuit yet. I'm probing the function generator directly, and I'm going to turn on the function generator now. Okay, so that's what mine looks like. Now, my scope probe, I've got the little red switch set to 10x. So I'm going to go to my channel 1 menu, and I'm going to put that scope probe on 10x. And then I'm also going to turn the bandwidth limit to 20 megahertz because that'll filter out some high frequency noise if there is any. All right, so now got something on there, but you can see it's not triggered because see that yellow arrow on the right, that's the trigger level. It needs to be up, so I'm going to move it up. So now we're triggered on that rising edge of the square wave, but I'm only seeing part of the square wave, so let's move the horizontal so we see well, let's look at that many cycles. And I can turn the vertical scale up so that we expand this a little bit here. Oh, now I'm off screen, so I'm going to go back. And I'm going to move this ground level down to 1 grid above the bottom, because it's just going to help us later on. So I'm going to use this vertical positioning knob to put this right at 1 grid. Something's not right here. That shouldn't be minus 14.8 volts. See, my probe is at 10x. No, I guess that's right. Yeah. So let's put that at minus 15, and then I'm going to turn this. Yeah, okay, that's more like it. So at 2 volts per division, 1, 2, 3, 4, 5 times 2 is 10 volts. All right, so now let's use the measurement menu to make sure we're at 10 volts peak to peak. So here you see it, we're at 10.32, and I think that's probably going to be close enough. One other thing I wanted to show you with the measurement menu, I'm going to hit measure, whoops, and then type. That's what I wanted to hit. There is, if I rotate over, there's an amplitude. If I select that and then hit type again, you'll see the amplitude is closer to 10 volts peak to peak. That's because when the square wave comes up, it's overshooting just a little bit. If I were to zoom in on this, you could see that there's a little bit of overshoot. So the amplitude is giving you a more accurate peak-to-peak level because it's taking into account the entire portion of the square wave. And if I turn on averaging, I think what I'm going to show you here, let's turn on averaging and give it about, let's say, 64 averages. You're going to see that that amplitude hopefully with your function generator, it will also show something closer to 10 volts peak to peak. If not, you could make a slight adjustment on your function generator to get it closer, but I'm pretty happy with that. Okay, so I'm going to turn the averaging off again, just because I don't want to turn it on until I get the final waveform that I want. Okay, so now I'm going to turn off the function generator and hook it up to my circuit. So the clip lead goes to the 1K resistor, the red clip lead, and then my scope probe goes to the other side of the resistor, which is also the capacitor node, or not the capacitor, but the inductor. It looks like a capacitor. So I'm probing across the inductor. So the ground of both my function generator and the scope probe are connecting to the other side of the inductor, the ground. All right, so now I will turn function generator back on. And there you see a kind of a funny looking waveform. So what's going on here is on the left, when the square wave goes up to 10 volts, the inductor voltage initially spikes to 10 volts because its current can't change. And so it sees that 10 volts. But then as the inductor starts to change its current, then the voltage drops down to some steady state level. And then the function generator jumps down to 0 volts, and again the inductor current can't change instantaneously, so its voltage has to spike down, and then it comes back up and then repeats the cycle. So what we want to do is we want to measure this charging cycle more precisely. So what I'm going to do is I want to spread this out so that I look at that charging cycle over pretty much the whole width of the screen here. So let me change the horizontal like so, maybe one more. Let's see if I can do it. Now I'm going to move this trigger point over to the left with the horizontal positioning knob. So let's move that over to maybe one grid off the left there. Right about there. And so I don't think I'm seeing the whole discharge, so I'm going to move the horizontal back one and then move this over again. So now I'm pretty much seeing the entire discharge. Now, one other thing you can do, you notice my peak level isn't quite full screen. And if I go one more knob or one more notch, it goes off screen. But what you can do is if you push this button in, it goes to fine adjustment, and then you could actually move this up so that you get almost to the top there. I'm going to put mine at 1.5 volts per division. So you can almost fill the entire screen with that fine adjustment, which is kind of nice. So now we're ready to take the measurements. But now I'm going to turn the averaging on, because that's going to clean up this waveform. You see how the trace kind of gets thick down here at the bottom. So if I turn on averaging now, and I'm just going to go for the gusto. I'm going to go for 512 averages. You could probably even do 1024. And watch what happens down here at the bottom. It's going to clean up nicely. And let me go to 10,000 or 1024. It's just, you know, we're gonna keep this waveform. I'm not going to change anything, so it's okay to do a lot of averages here. to clean that up. So now what we want to do is we want to measure what is the voltage after one time constant. So I'm going to put the X cursor right here. And so let's go to cursors. And I'm going to look at both X and Y. So this is highlighted. And I'm going to put X1 right there at that start. So X1 is highlighted, so I should be able to adjust it. Yeah, you see this moving here. I'm going to put it right on that rising edge. Okay. That's about as close as I can get it. All right, so now I'm going to move X2 over to one time constant away. So you should have calculated your time constant, which was based on your measured component values. Now just for this example, I'm going to use a time constant of 80 microseconds. Your number might be slightly different than that, but that's what I'm going to assume my tau is. So I'm going to move X2 to be 80 microseconds away from X1. So I need to highlight X2, and it's going to move over. Whoops, that's not what I want. You see what happened? It changed it to X2 minus X1. So now I got to start over. Go back to X1. Put that back where I want it. Now go to X2. Carefully select it so that it is X2. Now I can move this over. So I want delta X to be 80 microseconds. There. So the distance from where it starts to there is 80 microseconds. So now I want to measure that voltage there. So we'll choose Y1. Well, first thing with Y1, let's measure the top there. I think you're asked to do that. Looks like I've got Y2 up there, but move Y1 up to the top there. So Y1, for me, I'm measuring about 10.02 volts for that initial voltage. And now I'm going to move it down to where I intersect that 80 microsecond mark. So about right there for me. So that's my inductor voltage measurement for one time constant. And you can see Y1 is 4.95 volts. If I got it, maybe I'll move it a little bit closer. You might be able to see it better. Hopefully I've got it pretty good there. So 4.92 volts for my 1 tau measurement. So then you're also asked to measure the voltage for 2 tau, 3 tau, and 5 tau. All right, so for 2 tau, that's 2 times 80. For me, it'd be 160. So now I would move my X2, select X2, and move the delta X to 160. So that's 2 tau. Whoop, right there. And then I would select Y1 again and move it down to the intersection, roughly right there. And so my Y1 now is 2.97 volts for 2 tau. That's the inductor voltage at 2 tau. And then you do 3 tau and 5 tau. So for 5 tau, I'll just do 5 tau. 5 times 80 is 400 microseconds. So put my X2, select it. I want to put delta X at 400. So it's going to be all the way over here. I went too far. There, 400. And now I'll choose Y1 and move it to the intersection there. best as I can eyeball it. Looks like mine's about 1.8. So that's 5 tau, my voltage. And now I think you're also asked to measure the steady state. So the steady state is going to be, where it's exactly flat. So if I move it down a little more, my steady state looks like about 1.74. All right, so that's pretty much it for the inductor charging or storage measurement or measurements. Let me know if you have any questions.